Okay, the recording is now started. All right. So in this case, one set has A, D, B as its elements. The other one has A, B, C as the elements. B is an element of A, not true. None of the other answers. Maybe. B is a subset of A, no. A is a subset of B, no. A is an element of B. So in this case, it is none of the other answers. All right. So do we have any questions about number one, why it is none of the other answers? Okay, all right. So number two, we have A union B. So we know the union is A, B, C, D, E. We know A minus B is C and E. So the way we can distribute the elements in A, B, there are a few options. Okay, so we'll take a look at each and every single option and ask you, is that a possible configuration? The first one is set A has A, B, C, D, E. Set B only has A, B, D, missing C and E. Okay, that works, right? Because A minus B is everything in A but not in B. This works too, right? Because the union will still be A, B, C, D, E, but you can also see how C and E are missing. Oh, no, no, I take it back. This is not possible because C and E are missing in A to begin with, so there's no way it can be in A but not in B. Okay, I take it back. Sorry. This one is not an answer because in this case, A minus B would have been the empty set because everything in A is also in B. This one would also be an empty set if you look at A minus B, because everything in A is also in B, even though B has some extra stuff, it doesn't matter, okay? So A minus B would have been an empty set in this case. This would work too, because A has only C and E, and B does not, okay? The key is what B does not have that is in A. This one cannot be possibly be the answer, okay? Because A is an empty set, so that means A minus B is guaranteed an empty set. This one doesn't work because A minus B would have been A, B, C, D, E because B is empty. And then for this one, I think that works too. Okay, because A, C, E, C and E are in A but not in B, so this will also work. So there are three of them, that match the union as well as the quote unquote difference operator in the question. So are we okay with this one? Yes. Okay. All right, so now we move on to question number three. Choose the correct answer. A is an element of a set that has a set that has A in it. The answer is false. That is not the case. The only element in the set on the right-hand side of the element of operator is a set itself that has an element of A. Okay, so that's why the answer to this question is false. Yep, then it would have been true. Yeah. In other words, if the left-hand side also has braces around the A, then the answer would have been true. That would still not work. That is correct. That would not work. Yep. hmm I probably won't look at it from the syntactical perspective. I would look at it as a set with element A does not equal to, okay, I take it back. The value A does not equal to a set that has A in it. And that's it. Yep. So I think the equality has to do with, is the value A the same thing as the set, a set that has a value A in it? And the answer is no. Okay. So are we okay with this one? Okay. All right. Moving on to question number four. Choose the correct answer. Um, okay, that's an easy one because we only have two choices. You have a 50% chance of randomly guessing the correct answer. But since you can only submit once, you can't use that approach. So ABC is a subset of the set ACB. That is actually true because everything on the left-hand side is also found on the right-hand side. That is the kind of the interpretation of subset of in this case. Question number 5. So we want to look at the union of these two, and the answer is false. The answer is false because you cannot have repeating or the same value cannot appear twice in a set. So that's why the answer is false in this case. In fact, the right hand side is not a valid set in this class. Okay, so you cannot establish that equality. Question number 6. So this is where things get a little bit more interesting, okay? Because I'm not even telling you what is in A and what is in B. We just know that A and B are sets, and we just want to know if A minus B is an empty set, does that imply A is a proper subset of B has to be false, okay? So now you have to think of scenarios, okay? Now, what what goes through your mind when you read this question in order to guide you to okay, I need to consider these cases. What was the first thing that came to your mind? Hmm? Okay. So did you okay, go ahead. Hmm? No, I did not tell you anything about A and B. Yes, go ahead. Hmm. Okay. That would make the left hand side of the implication true. So you're on the right path. Okay, so there was another hand. Oh, okay. All right. So the key is implication. Okay, the implication operator is the key because if the left hand side of an implication is false, then the implication is true anyway. So it is not going to be very helpful to tell us which of the following is the answer. Okay, the only thing we can probably rule out in that case is since we can quite easily make this equality false, so that means the implication is going to be true, so we can just rule out the middle one. We can rule out the case that it is false regardless of how A and B are defined. So now we got two cases. We have either true or false, or true or it depends on how the sets A and B are defined. So now we have to say, can we make the left-hand side true, but the right-hand side false? Okay. So to make this true, as you said, you just have to make A and B the same. Then, the result is going to be an empty set because if A and B are the same, then everything in A that is not in B, there'll be nothing. So that means the empty set, the equality would hold. But in that case, A is a proper subset of B would also be false, but not false is true. So that does not make the right hand side false. So what you need to do to make the right hand side false is you need to make A is a subset of B true. So that not true is false. But at the same time, you also need to make A minus B equals to the empty set true. Okay? But that can be arranged by just making A having two elements, okay? Obviously not the only way to make that work. And then B has everything in A, and then just give it a third one. That will work. Because in this case, A minus B is still an empty set because everything in A is still in B. It make it makes the left-hand side of the implication true, but at the same time, A is a subset of B is true. But the negation of true is false. So now we have true implies false, which means the implication itself can be false. But it can also be true if I just add one more element C to A, then the implication is true. So that means it really kind of depends on how we define the membership of A and B. So that's the approach. So do we have any questions about this? Okay. I am guessing that if you put this into any type of AI, Gemini or ChatGPT, it would probably come back with a correct answer as well. Okay, it's just that by doing that, you are not going through the thinking process that is actually needed in order to truly absorb the meaning of the operators. All right, moving on to question number 7. Okay, so question number 7 says, what is the value of the following expressions? Okay, so in this case, the answer is true. It is regardless of how A and B are defined, because A intersecting with B would be things that are common to both. A union B would be things that can be found in at least one of the two. If they are the same, okay, just intuitively, it means that A and B have the same elements. Because if they do not have the same elements, then there will be something in the union that is not in the intersection. Does that make sense? Are we good? All right. So question number 8, moving on. I think that's the last question, and which is what you want to ask. All right, so this one is asking what is the value of the following expression? Okay, as a set is an element of B, implies it is not the case that A is a subset of B. Okay, so once again, it's very easy to make A is an element of B false. Okay, how can we make it false? Well, that's pretty easy. If A is an empty set and B is an empty set, that pretty much guarantees the left-hand side is false, right? Because an empty set has no elements. So nothing can be in B if B is an empty set. So that means we can rule out one of the three choices automatically. We can rule out false regardless of how A and B are defined, because I just found a case where the implication itself is true. Now, for people who are wondering, I hope there's no one. I hope the people who are wondering about this question is an empty set in this class, okay? But I'm gonna spell it out. So if someone is wondering what is implication, why with an implication, if the left-hand side is false, then the implication is automatically true. If someone is thinking about that at this point of this class, I would be concerned. Okay, because the implication operator is actually central to many definitions that we are going to have to look at in this class. Okay, so for those people, hopefully it's an empty set, right? Um, Making sure that you understand all the operators is really important. Okay, so I keep telling people all this. Okay, I know I may be just talking to the void, which is okay. Okay, just in case the set that I was mentioning earlier is not empty, that way I am still warning a few people about what they need to do. Okay, so now the big question is, how can we make the left-hand side true, but the right-hand side false? Okay, so that's what we need to do. So we'll go ahead and say, okay, how can we structure this so that, uh, okay, all right. So we'll go ahead and structure something that is simple. Okay, so we'll still make an empty set. Okay, Um, yeah, A being an empty set is going to be easy. Okay, so we make B a set of an empty set. Okay, so in this case, in the second case, A is an element of B is true because an empty set is a member of a set that has an empty set as its member. Are we good so far? So that's a really kind of important concept, okay? Differentiating, you can have an empty set, but the empty set itself can be a member of another set. It's just like you can have an empty folder, right? In a file system. You can have a folder that contains another folder that is empty. Okay, so if you think about a set like a folder, that analogy works for a lot of concepts, okay? But not all, but a lot. Okay, so this will make the left-hand side true, but the question is, does it make the right-hand side false? Well, the empty set is a subset of any set, right? So that makes A being a subset of B automatically true. Not true is false. So now we have a scenario where it is false. So that answers the question of, um, it can be false. So we can now say, okay, this is ruled out now. Okay. because it cannot be always true because I just found a case where it is false. So by elimination, the third option has to be the answer. Are we doing okay so far? All right. So it is the process of elimination in this case, being familiar with the operator and also the symbols for set related operations is really important in this homework assignment because without understanding the symbols, there's no way somebody can actually get to the correct answer. All right, so let me check, see if I'm getting the perfect score. Uh, okay, good, good, good. Okay, well, I think yep, so that's the key. Do we have any questions about this homework assignment? No, because an empty set, okay, so there are two rules or one rule that makes it not possible because one value can only exist once in a set because you cannot have duplicate values. Yep. Alrighty. So now we can continue with the discussion that we started on Monday. And that is, so this is where we left off last time, okay? So we talked about the first, okay, let me use a mouse pointer. So we talked about this expression already, okay? So now we're going to say, but this expression actually says exactly the same thing, okay? Even though it does not even look like that, okay? Um, this is about injection. So the best way to illustrate it is to use an example. So the way we can use an example would be I can find an example where it is an injection, find a different one where in which it is not an injection, and then we just kind of go through all the possible things that we have to go through in order to qualify whether it is injective or not, but not using the first definition, but using the second definition, which is where the mouse pointer is. Okay, but before we do that, let's see if we understand what this means. This is a quantifier. It says that for every q in y, not in x, okay? This is all in y, which is the codomain, okay? Because we have already asserted that f is a function because it doesn't make sense to talk about whether something is an injection when f is not even a function to begin with. So we already know that f is a function. X is the domain, y is the codomain. So we are now saying for every element in the codomain, this has to be true. What has to be true? Something has to be less than or equal to 1, which means it can be 0, it can be 1. So what is that something? It is the cardinality of a set that we are constructing. What set are we constructing? We are looking at the tuples PQ, where Q is already fixed by the quantifier. So P is the only one that is free, whereas, or you know, where PQ, that particular two tuple is an element of F. Okay, so that's how we read this entire, nested um, statement. So the question is, how do we evaluate it? Okay, so I'm going to give you some examples. We can keep this one as an example, but I want to kind of work through the cases that you have to work with. So hopefully this will help you. This Joplin is a great tool for taking notes, especially once you know how to enter the equations. Um, um, the way we enter the equations is called LaTeX, LaTeX, okay, but it's pronounced as LaTeX, not LaTeX, okay, because it really is LA, okay, because that's the initial of the person who came up with LaTeX, and then the the next three letters are actually Greek. It is tau epsilon chi. Yes, it's exactly. And tech, TEX, okay, tau epsilon chi, was a tool that was developed by Donald Knuth, who was a full professor at Stanford University. So he developed that tool so that he can write his paper, with all the notations and whatnot. So we are still using that notation, because that is so uh, established in industry. So we are still using that notation. All right. So the first thing is I'm gonna take this thing here and make a little snapshot of it, just so that this way we can keep it in our view. So this is a usual tool that I use, just to take a snapshot. So, and I can also make it always on top. So this way, I can, switch to a different screen without, making this one disappear. And now we can switch back to Joplin. So if you have not used Joplin, you can experiment. It is free. It's kind of like Obsidian, but it's entirely free. Obsidian is free too, if you just use the tool. If you have not used Obsidian or Joplin, um, I encourage you to at least kind of give it a try, because as a note taking tool, it's actually quite useful. Okay, especially if you can type a lot faster than you can write. Okay, this is actually a really great tool for note taking, but it does require a certain amount of mastery before you can use it effectively as a note taking tool. Okay, so what I'll do is I'm going to put in the assumptions. Okay, so I'm typing on the left hand side using Markdown, and if you don't know what is Markdown, you probably want to learn it. Okay, it is not a requirement to graduate with your computer science degree. Okay, but you really don't want to do just what is needed to graduate. Okay, not anymore. Okay, that is not going to get people anywhere. So Markdown is basically the de facto standard of documentation these days. Okay, if you go to GitHub, every README is a markdown. Okay, in terms of the source code, it is a markdown. It's essentially a shorthand for HTML, but it is a lot more readable just in the source format. Okay, if you don't format it, it's still really readable. So that's why your Markdown is such a great tool. All right, so we're going to look into, okay, this is how we start the equation. So I'm going to just copy the same thing over here. We are mapping from AB to 1, 2, 3. So we're going to say X is the set that has AB in it, okay? And then we also want to say, Y is the set that has a 1, 2, 3 in it. So you can actually see how the left-hand side, which is, the actual markdown is, rendered on the right-hand side. You can focus on the right-hand side. You don't have to look at the actual markdown. But if you want to learn markdown, okay, this would be a way for you to learn it. And we are going to assume a certain f in this case. So we are going to say, what if AB, oh, okay, that cannot be AB. What if A maps to 3 and also B maps to 3? Okay, so we're going to look at this particular example. The first thing we have to ask is f an actual function, with X being the domain and Y being the codomain. So this is basically a quick check of whether you understand what makes a set of two tuples a function. So can someone tell me whether this particular f is a function or not? Yes. Hmm? Okay, so there are two requirements, okay, from the previous class. There are two requirements. The first one is f a subset of the Cartesian product between x and y? That's the first requirement. And I think it is, right? Because A comes from X, um, 3 comes from Y. So the first element is, in the Cartesian product. The second element, B is also from X, 3 is also from Y. So both elements meet the requirement of the first item of the two tuple has to come from X, and then the second item of the two tuple has to come from Y. So it is in fact a subset of the Cartesian product between X and Y. But there's a second requirement to become a function. We have to verify that every element in X or the domain maps to one and only one element in Y. Does it meet that requirement? Okay, why are you shaking your head? But that still meets the requirement of one and only one. One and only one does not imply it is unique. It is just a counter. Yep. So in this case, A maps to 3, and we ask the question, Does it map to anything else? No. So that makes it meet the requirement of one and only one. What about B? Is B not mapping to anything that will make the count 0? No, it maps to 3. Does it map to anything other than 3? No. So that also meets the requirement of one and only one. Okay, so f is indeed a function in this case. So now we have to evaluate this expression here. So I'm going to break this down into the smallest possible step, but I'm going to warn everybody, I will not share this document with you. You're going to have to write this down, okay? Because I don't want to take your notes. That is your job. My job is to present it. Are we good? Okay, and I will give you time. Okay, I'm not going to fly through this whole thing. I'm just going to give you time, but you have to write down your own notes. Okay, I will not share this document with anyone in this class. So you have been warned. So the way we evaluate this is we have two cases. Okay, because, oh, actually, I take it back. We have three cases because the quantified expression says for every q in y, how many elements are in y? There are three elements, right? One, two, three. Those are the three elements in Y. So that means we have three cases that we have to evaluate. The first case, okay, the first case is what if Q is the first? Okay, I can do this out of order, and I'm going to intentionally do it out of order. So the first one is Q is 2, and then the second one is Q is 3, and then the third one is Q is 1. Are we doing okay so far? So we are kind of running a loop, okay, for every element in for every element Q in Y, we have something to evaluate. So there are three cases. We good? Okay. So now what we do is we go back to the case when Q equals to 2, and then so this is the other thing you can do is to do indentation. Okay, so we have a indented or nested bullet point list here. Okay, so when you're writing this in your notes, okay, you can use arrows to kind of point to different places because I'm not doing this linearly. So now we ask, okay, when Q is 2, what happens to the expression in the parentheses? Okay, so now we basically say, okay, what is the set, okay, dollar, what is the set that says, every element is going to be a 2 tuple. I don't know what P is, but I know what Q is. Q is 2. Such that um, P2 is in the set of F. Okay, so this is the first thing we need to calculate. Is that okay? Does everybody understand why Q is now substituted with an actual concrete value of 2? Because we're only evaluating that one single case as one of the three subcases. But for this particular subcase, we're only focusing on what if Q equals to 2? So what would be the answer to this question? Can someone come up with the actual answer? What is the membership of this particular set? What element of F is a two tuple in which the second item is a value of 2? Okay, so the question is, what element in F is a two tuple such that the second item of the two tuple is 2? None of them, right? So that means this is the answer. We're looking at the answer here. So once we resolve what is the set itself, now we can evaluate the cardinality of that. Okay, so now we say, okay, what is the cardinality? Okay, I have to do this. So what is the cardinality of an empty set? It is it is 0. Very good. Okay, so now we evaluate, is 0 less than or equal to 1? Yep. Okay, is true. Okay, I'm going to use 1 to represent true. Okay, so that means for the case where Q equals to 2, we're all good. Okay, the requirement is satisfied because we are looking for the ad hoc set to have a cardinality of 0 or 1. So it's fine. It's all good. So now we move on to, eh, we, I'll just move on to the next one here because this is going to look almost exactly the same. So I'm going to use the lazy way to do this: copy and paste, change all the twos to ones, and everything works out the same way. Because if you look into F, okay, we're really asking how many of the elements of F is a two tuple that has a value of 1 for the second value of that tuple. The answer is 0. Okay, so that means that the same logic works for q when q equals to 1. So now we go back to the case when q equals to 3. So we will, I'm just going to be a little lazy, copy and paste. Okay, but this time we're looking for two tuples where the second item is a 3 as an element of F. So now the question is, what is the result of that? It is no longer an empty set. In fact, there are two elements, right? Because the entire F meets this requirement. A3 is a two tuple that ends up with a value of 3, and then B3 also meets the same requirement. So that means the next thing we need to do is to look at the cardinality of the set that we were just constructing a little bit earlier. So we are now looking at the cardinality of the set of A3, B3. Okay. So what is the cardinality of that? It is a 2. And then we now that we know the cardinality, we compare the two and we ask, is it less than or equal to 1? The answer is false. That is not the case. So that means we have one case, okay, of the three, we have one case where the condition that we need to evaluate for Q is false. And can someone remind me again, is this universally quantified or is it existentially quantified? It's universally quantified, which means I need that to be true for every case in order for the quantified expression to be true. If I find one that is false, that ruins the whole thing. So that means in this case, the way I define this particular function f, it is a function, not a problem, but it is not an injection because the quantified expression that we are evaluating here is false. Are we doing okay so far? Okay, so I will give you guys enough time to copy if you wish. And I can just kind of expand this so you can see the entire thing. The most important part is the meaning of the universal quantifier. Okay, we have to evaluate that expression for every single case, and then for each case we come up with a Boolean value, either true or false. If everything is true, then we are all good. The quantified expression is true. But if at least one case gives us an answer of false, which in this case is the case when q equals to 3, then the universally quantified expression is false. So this is the reason why this particular function f is not an injection. All right. Do we need more time to kind of copy this? Okay. So when you're copying, okay, or when I work on this, you can also kind of jot down some notes about your own thoughts, okay? Because that's the one thing that I cannot record in the recording. So your own thoughts should be a part of your notes, okay? What you how you connect the concepts back to the concepts that we have already talked about, that connection is what you really need to write down, okay? Because otherwise, it's just a whole bunch of symbols. It's meaningless when you read it. All right. So now that we are done with this part, I will give you a different example, okay? So this time I'm looking at the number of lines. I don't think I can do this. Yeah, it doesn't understand, number of lines. That's okay. we'll go ahead and do it this way, and then we just paste. No, it doesn't like to do that either. Okay, so let me see what we can do here. Oh, I just, that was my mistake. Nope, it doesn't want to do it. Okay, I have to do some counting here. So 12, 13. Okay, there we go. 13YY. Do a paste. Yep, okay, that works now. All right, so we have a new case. And in the new case, we are just going to make some minor change, make a minor change to the membership of F. Okay, so this is a second example. So in the second example, and I'm just going to make sure that we understand this is a second example. Okay, so we'll go like here is another example, just to be sure that we are separating the two. So in this case, okay, when q equals to 2, we end up with exactly the same answer, which is cool. But when q equals to 3, we don't have a A3 anymore. So this particular set only has one single member, which is B3. So that means the cardinality becomes a 1. And since we are looking at 1 is less than or equal to 1, the answer is actually true in this case. Are we doing okay so far? Okay, it's basically the same reasoning, but the membership of the set that we are constructing ad hoc has changed its membership. So now we look at the last case, which is when q equals to 1. So when q, okay, I want to show as much as possible here. So when q equals to 1, um, the number of elements of the set that we are constructing is no longer empty because A1 as a two tuple meets that requirement. And as a result, this particular set also has A1 in it. I have to go back to change the previous one because I forgot to take out this one. So now we have a cardinality of 1, and 1 is less than or equal to 1 is actually true. So in this case, all three cases, okay, no matter which element of y we are looking at, the condition that we need to evaluate returns a value of true. So that means this one is injective. All right. So I'm going to let you guys, write down some notes if you need to. Yep. So you can say one of two things. You can say the function is injective, or this is an injective function, or you can say it is an injection. So an injective function is the same thing as an injection. Yep. All right. So I'll be understanding, how to evaluate a universal quantifier in this particular context. We're good, okay? Because this actually illustrates a few things, okay? It shows how we construct a set on the fly, which in the expression is from this brace to this brace over here, okay? That's how we construct a set on the fly. And then we also talk about, the quantifier, okay, the universal quantifier. We have three cases, and we have to evaluate every single one of those cases and make sure that every single one ends up with the answer of true. So this one is not a counter. It is this one means true, this one means true, this one means true. The other side is a Boolean expression. All right. So are we okay with this example? You good? Okay. So now we go back to the notes. Okay, we go back to the reading material, and I claim that this thing here is really the same thing over here. Okay, so the first one we talked about on Monday already. Okay, we talked about this one on Monday. It is basically saying, okay, if I pick okay, if I pick P as an element of the domain, Q as an element of the domain, if they are the same, I don't have anything to do because if they are the same, then P does not equal to Q is going to be false. And if the left-hand side is false, the implication is true. So I don't have to think about that one. But when P and Q are different, then I also need f of P not to equal to f of Q. So that turns out to be meaning exactly the same thing as what we just did here. Okay, does that make sense to you? So let's take a look for people who are more visual. We can look at this from a more visual perspective. Okay, so we can have two things in X. We have three things in this case in Y. Injection means everything in X has to point to something that is unique in Y. What is the other way to say it is unique? Not two things from X can point to the same thing in Y. Or you can also say, well, okay, I shouldn't say not two. I have to say the number of things in X that can point to the same thing in Y cannot exceed one. Does that make sense? And that's basically what the second expression is trying to capture. It is basically saying for everything in Y, the codomain, the number of things from X that can point to it is at the most one. It can be none. None is fine. Okay. So that means if you think about it that way, so that means this is cool. Okay. Even though the third element has nothing from X pointing to it, that's okay. Because that means the cardinality that we are looking at here is just zero, which is fine because zero is less than or equal to one. But when you look at the two things in Y that are mapped from X, there's only one thing in X mapping to it. So that means the cardinality is only one being less than or equal to one. It's also cool, not a problem. So when do we have a problem? We have a problem when we have at least two items from X pointing to the same thing in Y. Because in that case, when we count the number of things in X pointing to that one thing in Y, it'll be two, which is more than one. And that is not cool if you want the function to be injective. Are we good so far? All right. So there are multiple ways of looking at things, and this is just one alternative way of expressing the same thing over here. Are we doing okay? Yep. Or an infinite number of elements, right? So when you have an infinite number of elements, then you have to rely on the structural mapping from the domain to the codomain, because in those cases, typically there's an equation of some kind to establish the mapping. So we'll get to that. Okay, we'll get to that. And there's sometimes you can also use some other arguments, even though they may not be completely mathematical, but they can still be completely logical. They can still be rigorously logical. So as long as the argument is logical and is rigorous, it's still okay. So we will see cases like that later on. All right, so that's injection. Okay, so now we move on to surjection. So surjection is expressed here. Okay, so once again, there are two ways to express the surjection. This is one way, and this is the other way. So we focus on the other way first, because we go like, tech, that looks like what we were just working with. Almost, but not exactly the same. Okay, because what we were looking at for injection is still here. So now we just compare these two. Uh, okay, fine. I was about to say side by side, but this is side by side. But actually, top down is easier because everything aligns and it's easier to see the differences versus the what is common. So what is the difference? What is the one single difference? Yes, greater than or equal to 1 instead of less than or equal to 1, right? So that means, okay, so what does that mean? So this means for every element in the codomain, we need at least one thing from X to map to it. Okay? In other words, everything in the codomain are used. That's basically what it's saying. Okay? So that's one way to look at it. The other way to look at this is to look at this expression. So this is the first time we see the outer one is a for all, and then the inner one is a there exist. Since all of you have taken pre-calc and many of you have taken Calc 1 at least. So that means you should know the delta epsilon description of limits. Is that correct? No? It's been a while. Okay, that's okay. I mentioned that only because it also has the same kind of structure. There's a for all on the outside, and a there exists in the inside. Okay. Okay. So let's first talk about how do we say this in English. It says for every q in y, there exists a p in x such that f of p equals to q. That's what it says. Is that okay? But in the other way to interpret this is everything in the codomain, which is Q, is mapped to. If I randomly pick one thing in the codomain, I should be able to find at least one thing from the domain that maps to it. That's basically what it's saying. Because there exists does not really care whether it's one, two, or three. It just says cannot be zero. It has to be at least one. Yes, go ahead. Yes. Yep. So, but in this example, when we have more things in the codomain than there are things in the domain, it is guaranteed not to be surjective. Yep. hmm So this in this particular scenario where A is only has two elements and B has three elements, and we have a function that maps from A to B, that function is guaranteed not surjective because there are not enough things in X or in the domain to map to the things in the codomain. That is also called the pigeonhole principle, which we'll also talk about later in this class. Are we good so far? All right. So, do we want to dwell in surjection or are we ready to move on? Because the difference between surjection and injection really is just, the less than or equal to one become a greater than or equal to one. Are we good or not? Okay, I got some confirmation we're good. Okay, excellent. Okay, so we are moving on because if you really need more time to talk about this, you need to let me know. I am not a mind reader, and you should thank me for not being a mind reader. Hmm? Yeah, that's fine. I mean, the formula is in the notes. All right. But writing it is actually helpful too, because the more you actually write it, whether you're typing it or writing it in your notes, the more you're actually trying to map those symbols, to the meaning of those particular symbols. All right. Mm, So we good? All right. So now we move on to bijection. Okay. So bijection, once we have introduced injection and surjection, bijection is actually easy because a bijection is a function that is both injective and surjective. That's all it is. Okay. Once we understand injection and once we understand surjection, bijection just means, as you noted a little bit earlier, can a function be both? The answer is yes. Okay. And the functions that are both, they're called bijections, and they have some special interesting properties. So just quoting, the universally quantified expression earlier, we need this to be true, and we also need that to be true. In other words, if I want to be lazy, I just have to say, okay, this cardinality has to be less than or equal to 1 and also at the same time greater than or equal to 1. Yes, which means it equals 1. That is correct. Okay. So, what kind of special thing is about that? Okay. What happens when this expression equals to 1? So that means we have a one-to-one correspondence. Okay, so this is actually the end result. So you look at this one and you go like, but heck, we have seen something like this already. That is the second condition for a uh, subset of the Cartesian product to be a function with one minor difference. The minor difference is the other one is saying for every element in the domain, this has to be true. This one says for everything in the codomain, it has to be true. Okay, so let me point back to the module that we talked about on Monday, just so that we have a point of reference. Okay, give me a little bit of time. Um, this is about functions, and I think it's in this section somewhere because I derived it in the class. Okay, I do not use exactly the same symbols, but close enough. Okay, so I'm gonna do the same trick here. Okay, because I need this to be presented uh, as I switch back to the other note. So I'm gonna put this one always on top, and then switch back to the module here. And then now we can do a compare. Go like, okay, so what is the same and what is the difference? Okay, there's only one difference. The difference is one thing says for every element in the domain, the other one says for every element in the codomain. That's it. That's the only difference. Okay, but this affords us some really interesting thing because now we are guaranteed for every function that is a bijection, we're guaranteed an inverse function, which means if you know where in the codomain you land, you know where you came from. Yep. Nope, you cannot. If a function has an inverse function, it has to be a bijection. Yep. By the very definition, you need a bi. It needs to be it needs to be a bijection. Yep. Okay. So the last sentence is exactly what I just said. Okay. Not in exactly those words, but implying the same thing. Bijections are important because it implies reversibility, which means there's an inverse function. Okay. Um, a function that is bijective has an inverse. Okay. So let's take a look at functions that are bijective and see how we can kind of reverse the operations. Okay, so I'm going to, well, okay, we'll just move ahead first and then we'll kind of come back to take a look at the other example. Are we ready to move on? Okay, okay, cool. All right, so I'm gonna take out this thing here because that's really just copying from an earlier module. Okay, so I'm gonna take that out and then we're gonna move on. All right, so here's the inverse. So for any particular reason, for any reason that you cannot copy as quickly as you would like, and I'm moving on and you're too shy to raise your hand, the best thing to do is to note the time because you know that I'm recording, right? So if you know the time when we talk about this, you can watch the YouTube recording, go fast forward to exactly that moment in time, and then freeze the frame, and then you have all the time in the world to copy whatever is on the projector. So that's one thing that you can do with this class that you may not be able to do with some of your other classes, because if the professor is not recording everything on the projector, then you cannot use that technique. But in this class, you might want to check with me first, okay? Are we recording? Okay? Because if I forget to click the record button, which has happened in the past, then you cannot use that method. All right, so inverse. So this basically just says, how do we create the inverse function? Um, so this is how we define the inverse function, knowing that f is a bijection. Okay, so this does not work if f is not a function or f is not a bijection, even if it's a function. So knowing that f is a bijection, this is how we construct, the inverse of the function. What is it saying is for every p in x, for every q in y, pq is in f if and only if qp, you can see the reversal in the two tuples, if and only if qp is in f inverse. So that's basically how we construct an inverse function. So maybe an example would be helpful, right? So the example that we're going to use We can just kind of use the example already in Joplin. So this saves me a little bit of time. We can just kind of go with this one. So because we look at this one, it's not a bijection because this particular F is an injection, but it's not a surjection. Can someone tell me why it is not an a surjection? Yep, because it is not the case, right? So which one is not bound? Which one is not mapped to? Exactly. So 2 is an element of the codomain, but yet nothing from the domain maps to 2. So that means it is not a surjection. Okay, very good. Okay, all right. So now we have to create a third example. Okay, so we'll go ahead and copy and paste this. Okay, and we'll take a look at an example of a bijection. All we have to do is to take the element out from the codomain. Now everything is all good. Okay, let me scroll down because you can only see the Joplin side, the markdown side, but not so much the rendered version. Okay, so this is the function that we're looking at now. X as the domain has AB, Y as the codomain has 1, 3. So now the same F is now a bijection. Okay, so this is important. Okay, something that was not a bijection because there were too many things in the codomain. If I adjust the codomain, I can make the same set of two tuples a bijection now because it is also a surjection. Okay, so to create the inverse function, you just have to use, for every element in F, we just have to reverse the ordering, and now we have a inverse function. So in this particular case, F inversed, okay, F inversed has the following elements. I will intentionally make things out of order, okay, just so that we emphasize that ordering is not important at all in a set. So that would be the inverse function. Are we doing okay so far? Understanding, with a bijection, how do we create the inverse function? Good. Does that make sense so far? Okay. All right. Excellent. And if for those people who are thinking, so how is this going to be useful? We'll talk about that. Okay. So there are applications of this. All right. So that's all basically you need to know. Now we go back to the sorting example. Do you remember what I wrote the other day? Okay, we need to have a function to map the indexes, and that function needs to be a bijection. That was on the whiteboard on Monday. Okay, so now that we understand the bijection, that makes sense now because it's basically saying for every slot, okay, of the incoming array, whatever value is in that slot has to map to one and only one and unique thing in the output array. So if the original array is 131313, the output array has to be 111333. Okay, and there are multiple mappings in that case because we have 3 1s and 3 3s. So there are multiple ways to make that bijection work. All right, so there are some questions generated by the AI, and we can go ahead and go through some of these. And even the prompt is available to you. So if you want to generate your own, you can do so. Okay, so let's go through these questions. Okay, what does it mean for a function to be injective? Yep, 0 or 1 element from the domain that maps to it. Yep, that's one way to say it. The other way to say it is um, for any 2 element in the domain, they have to map to unique things in the codomain. Okay, so we'll see what the AI qualify as the answer. Okay, an injective function is one where each element in the domain is mapped to a unique element in the codomain. This means no two elements in the domain map to the same element in the codomain. Okay, so that's pretty good. All right, question number two. Is the function AB maps to A123 with F having the members A1, B1 injective? The answer is no, it is not injective because A and B both map to 1. Okay, so there you go. So there's the explanations. So this is helpful. Okay, if you want to kind of have a little practice, after reading the section or after today's class, I would go to the questions here. Okay, because it's already generated. For those of you who are a little bit more adventurous, you can actually use the GPT prompt and enhance it. It does not want to do that. I don't know why. I think it has to do with the version of ChatGPT or oh, the fact that I haven't signed in. Okay, I think it has to do with I haven't signed into ChatGPT. Um, but I can give you the prompt. I mean, that's not a problem. And I just lost the module because I closed the tab and I forgot to make a new tab. That's okay. We can quickly get back to that section here. There we go. Um, all right. So I think we are okay. Let's more on the use of set notations. Is that the right one? Yep, it is the right one. Okay. Given f is xyz going to 1, 2, 3, if we have x1, y2, z2, evaluate the injectivity or whether it's injective using this particular set notation. The answer is it is not injective because when p is y and q is z, then f of p equals to f of q, which means this not equal to is going to be false, which means the implication is also going to be false. So if you expand it, I think it should give you about the same kind of answer. All right. Now this is all done back when I was using I think ChatGPT 3.5 or 4. Now that we are up to 5.2 and Gemini is up to 3 already, if you ask the AI to give you some quiz, it's fancy. Okay, it is very interactive. It's multiple choice and it's colored and so on and so forth. So I would highly suggest that you give that a try. Yes. Um, I just use Gemini, or I encourage you guys to use Gemini because it's already available to you. I like Gemini better because I think it gives me more objective answers. Um, I don't see a problem with Gemini compared to ChatGPT. The big difference between the two is if you are cheap and you don't want to buy a book and you just want a summary of a book, Google is pretty good at respecting copyrights. So if you say, I just need a summary of a certain book, Google would go like, I don't have the book, I cannot summarize for you. But ChatGPT would go ahead and just summarize the book for you. So I found that that is one major difference between ChatGPT and Gemini. All right. So are we all good here? Okay, we'll go ahead and take row first. Okay, so we're gonna take row. This is row on 0204. I'll just go ahead and turn it on, and you will need the access code. The access code is bijection. So this is our access code right there. And then after this, I got some questions. Okay, you don't have to answer, but I'm curious. All right. It looks like most people are done. Okay. All right. So here's the question. How many of you um, were in high school when the pandemic hit, and it was about the time that you had to learn algebra or okay. So do you think the pandemic made a difference? It's hard for you to tell because you have to compare that to people who did not experience the pandemic when they were about to take algebra as a class. Okay, so let me ask you a different question. Okay, when your classes are online in a high school setting, does that mean that you don't have to take notes anymore? The answer is yes. Okay, and there's one more thing. Compared to an in-person class, if when you're taking a class online, does the online version of this very same class on the same material does it train your attention span so that you can gradually increase your attention span until you get to, guess what, 80 minutes in a college class? So those are the factors. Okay, so I want you to be aware of the impact of the pandemic. Okay, because one is the subject matter. Okay, did you learn algebra that you're supposed to learn in high school? Two, when you're in person, okay, in the high school, you will probably need to take notes. Okay, your teacher, your high school teacher, will tell you, okay, you need to take notes. And my kids actually had the teacher going through the notes that my kids took, and they would actually comment on the note taking techniques. And number three is attention span. Okay, because if you're taking a class online, you go like, okay, I have access to the material the whole day. I don't need to have a long attention span because I can just go back to the material whenever I want to go back to the material. And there's one more thing. Did you guys get a pass no pass? Instead of using grades, this high school changed to a pass no pass standard. Okay, I see people. So it's all graded like A B C D F. Uh huh. Okay. Yep. They went back to the ABCDF. Okay. Yep. Mhm. Mhm. Okay. Okay. So you're lucky. You got a responsible teacher. Ah, I see. Okay. So I just wanted to kind of get an idea because I was curious. Yes, go ahead, Ari. Oh, I thought you had a question or a point to make. Okay. So that is kind of interesting. All right. So with the remaining 10 minutes, we're moving on to Aleph Null, okay, the reading module of Aleph Null. And let me point out where we are at this point in terms of the reading material. The good thing is we have a whole weekend, so that means you have time to read it. So this is where we are at, okay? So we are now at Aleph Null, and it also means that I can give you another homework assignment. Okay, so there will be another homework assignment, which is just your functions. All right. So first thing first, we'll get to Aleph Null. Okay, so this is Aleph Null, which has its own module, blah blah blah, and so on. So this is when we look at the cardinality of integers versus natural numbers. Okay. Remember how we talked about this a little bit? I claim that they have the same cardinality, and yet one is a proper subset of the other one. Okay, so just to recap what we talked about in a previous class, we have established that the set of all natural number is a proper subset of the set of all integers. Okay, well, that's pretty easy to tell, right? Because when you look at a negative integer like -2, -2 is missing as a natural number, but it is an integer. But every natural number starting with 0 is also an integer. So, this is pretty intuitive. But I also mentioned something like, oh, but if you look at the cardinality, we consider these two to be the same. You go like, that is awkward, right? Because if one thing has quote unquote more things than the other one, how can the cardinality be exactly the same? So the whole thing relies on the concept of a bijection. Okay, so this is the immediate use of a bijection. Basically, what we say, okay, we don't have to write this down, but if you want to, that's all cool too. So basically, we say that there is a function g, there exists a function f that is a function that maps from natural number to integers, and f is bijective. Okay, so let me explain what that means. Okay, so what this means is I can find at least one way so that I can have a function that maps natural numbers to integers in a way that it is bijective. Okay, so let's look at something that is not bijective first. Okay, so things that do not work. So in this case, if I say f of x is just x, that is not bijective. Because what this is going to do is it will map 0 to 0, it'll map 1 to 1, it'll map 2 to 2, and so on. What about the negative values of the codomain? They are not mapped to. Yes. Okay. Do you want me to pause or do you? But there's no after that because there's an infinite number of positive integers. Yep. So that part doesn't work. Okay. So I'm going to give you the answer. Okay. I'll give you the solution, the f that does work. So this function does not work because it is not surjective. Is it injective? Yes, okay, because every x maps to itself in the integers on the integer side, so it is injective, but it's not surjective because nothing maps to the negative integers. So that means, okay, that's not going to work. Yes, exactly. Okay, so we use the even and odd. So what we do is we say, okay, give me a natural number. Okay, and then we say, well, depending on whether the natural number is odd or even, let me lower the table so people in the back can see the whiteboard. Okay. So if x is, okay, so I'm going to use C++ notation here. So if x mod 2 is a 0, then it is even. And if it is even, I will map it to, let's say, the non-negative side of integers. Okay, so I'm going to say, if that is the case, we are just going to map it to x divided by 2. If it is, if this is when it's even, when it's odd, we'll map it to negative values. So if x mod 2 is an odd number, that means I can just go like, we'll just kind of add 1 or subtract 1 from x and then divide it by 2, divided by -2. So this is the function. Before we go any further, what is the question mark and the colon doing here? This is something I borrowed straight from C++. And by this time, you probably should understand what is that operator. The ternary operator. That is correct. Okay. So does anyone in this class not have any experience or not know what is the ternary operator? Okay. Um, because CISP 400 and 360 should have introduced the concept of a ternary operator. Yep. I am so sorry that you learned Java instead of C++. Okay, okay. Um, I'm gonna ask this question. How many people took 360 or 400 from ARC? Okay, so everybody. Okay, maybe it's a recollection thing. Okay, then never mind. So a ternary operator is a three thing. Okay, there are three items. That's why it's called ternary because there are three. This is the first part, is a condition. If the condition is true, then this part is the value. If the condition is false, this part is the value. In other words, it is if then else in a single expression. Okay. So in this class and also in 310, the ternary operator is really useful because this way I don't have to use if then else. I just combine the if then else into a single expression. All right, so let's take a look at this function. We only have about 2 more minutes to go. So we're going to say, let's take a look at 3, okay? Where is that thing mapped to? So we now look at 3 mod 2, it's a 1. 1 equals to 0 is false. And then we go straight here, and then we go like, okay, -3 minus 1 is a 1. Darn, it doesn't work. Because I need that to map to I need that to map to -2. So we're gonna have to add a 1 here. I think that may be the other way around, but let's try this and see if it works. Okay. So if x is 3, 3 plus 1 is 4. 4 divided by -2 is -2. Okay, very good. What about f of 1? 1 is also odd number. 1 plus 1 is 2. 2 divided by -2 is -1. Okay, that seems to work. What about even numbers? Let's try 0 itself, okay? So f of 0 would map to 0 divided by 2, which is also a 0. Let's map f of 2, okay? So f of 2 is 2 divided by 2, which is 1. So do you guys see the way this is working? Okay? So I claim that this is a bijection, okay? First of all, do you think it is an injection? In other words, if I have two different values, do you think those two different values can map to the same thing um, in the codomain? Nope, I don't think that is the case. So now the next question is, if you look at it from the surjective perspective, if I just pick any integer on the integer number line, do you think I can find what on the natural number side maps to it? Can I have an inverse function? So what I want you to do, okay, because we are running out of time, so what I want you to do is to read the entire module, okay? Read the entire Aleph Null module. Certain parts of this can be a little bit tricky because it requires an understanding of the quadratic equation, okay? That's the hardest part of this, okay? So try to read the entire thing, and then on Monday we'll come back and we'll talk about this particular f is bijective, and that's why we can establish this equality here. But we'll also talk about something that is even more interesting. So the more interesting thing is the cardinality of just natural number actually equals to the cardinality of the Cartesian product of natural numbers. These two actually have the same cardinality. So that is even more interesting because if you look at a number line and you look at a number line, they have the same cardinality. Go like, I can see how that can happen, but I can actually fold a two-dimensional space into one single dimensional. Okay, so read the module because that is actually kind of interesting. And when you're reading it, you can skip the derivation if you want to, but I think the derivation is actually the most important part of what you're learning here. So that's up to you. All right, so that's that. I will see you all on Monday. Have a nice weekend. Unless you're also in my 310 class, then I'm so sorry that I'll see you again. I'm sorry for you, not for myself, by the way. All right, let me stop.